All right, so in this video, I'm going to be talking about this theorem. So this is a theorem of mine. It's from a recent preprint I put out, and it's kind of misleading to say that it's a generalization of the Takhtajan-Vinogradov results for the classical additive divisor problem because for these assumptions, you can't actually reproduce that case, right? So I am going to be doing everything for level n prime, right? Takhtajan Vinogradov, they do it for level 1. I have these Dirichlet characters, and they have to be non-trivial. Of course, Takhtajan and Vinogradov had trivial Dirichlet characters. And then I'm going to have these complex numbers, u and v, that come in. These are going to be sort of the subscripts of the divisor sum functions. And I say that they must be non-zero. Of course, Takhtajan and Vinogradov took them to be 0. And then, okay, with these assumptions, I get the following asymptotic, where here tau is the Gauss sum. And it looks asymmetric, but if k is coprime to n, then you can use the functional equation for the sum of divisors function and make these two terms look the same. Well, the same up to, u goes to minus u, v goes to minus v, and putting a conjugate over these things. So this video, I'm going to give closer to how I give seminar talks for this result. So that means I'm not really going to assume too much background. I'm not going to be assuming that you've been following along closely so far, and it's going to have a lot of background stuff that did come up in previous videos. And it's also going to skip over some details. In future videos, I'll go over those details more carefully, but this one is just a general overview of how one obtains this result. So for these assumptions, I should say that the assumption that n is a prime, as opposed to letting it be general, this is not a serious conceptual obstruction. This is just for ease. Ultimately, this means that gamma naught of n is going to have two cusps, and you can do it with just a little bit more technical manipulation, but the simplest case after level 1 is prime level, and that's why I chose to do it. Then there are these other assumptions, the complex numbers be non-zero. If they're 0, then you know that the Eisenstein series at s equals 1/2, it has a y and it has a square root y and has a square root y log y in the constant term. And so you'd get some log y's appearing here, and then this would give you powers of log next to your x. So the growth would be different, but you can also deal with that case just by keeping track of that stuff. And so, a lot of these assumptions are really just for ease as opposed to being some limit to what the technique can handle. So one thing that's kind of neat about this is that often for these additive or these shifted convolution problems, so a shifted convolution problem is something like when you take a sum of some sequence of arithmetic interest times that sequence of arithmetic interest but shifted by some constant amount, you get maybe an asymptotic growth of c times x to the r for some r, and then you'll get this error term, which is going to be x to the r minus something, and then maybe a plus epsilon, whatever. And often the question mark is 1/3. So we saw that in the Takhtajan-Vinogradov result, where you got a growth of x times log x squared, and then you had an x to the 2/3 plus epsilon here. If you look at the error term here, you can do a bit better. So these are called shifted convolutions, I should say. And so here you can do better here, taking, and then you want to take u and v to be, I believe, if they're very close to 1/4, or maybe it's one of them you take to be 1/4, one of them you take to be minus 1/4. No, it should be, I don't know, something like this. Then, or maybe it's, okay, I'm not sure. But there's some combination, taking the u of v as the extreme points, that you get a little bit better than a 1/3 power saving here, which is kind of cool. The techniques are the same as what you normally see, so there's nothing really too special going on, but it is cool to see an example where you break this 1/3 barrier. So shifted convolutions, there's this question of why do people care? And there are some applications. And for example, one of the most important applications are subconvexity bounds. So a subconvexity bound is something about the growth of L functions on the critical line. And if you can get a bound, if you can say that it doesn't grow too quickly, then you have a subconvexity bound. And this also, related to this, is moments of L functions. So this is basically saying growth of L functions in the critical strip, shifted convolutions come up. You can imagine that if you square an L function, then you have these sort of off-diagonal terms that come up, and you're going to need to deal with them. So you're going to need to know how they grow. But also, it's just interesting, right? So it's interesting for its own sake. Right, you can think of this as a question about correlation. It's the correlation between the value of whatever whatever sequence you have at some integer and that sequence at a few integers over, a shifted, constant number over. You can imagine that if this is a divisor counting function, then you're asking about the correlation between the number of divisors of n and the number of divisors of n plus k. Or, if you're told that n has a lot of divisors, then does that tell you something about how many divisors n plus k has? Does it have more than you would expect, fewer than you would expect? That's kind of an interesting question. And so I like these shifted convolution questions just for their own sake. I think they're inherently interesting as statistical questions. So this is the result you get, and I think that this normalization also, I should say, is very natural because these sum of divisor functions have a functional equation, and this is the normalization you would expect for that functional equation. So it's a very natural quantity that comes up here, and giving this asymptotic growth for this correlation, I think is pretty cool. So how does one prove such a thing? So I'm going to give this identity a name. I'm going to call it star, and whenever I refer to star, I'm referring to this equality right here. So the idea is going to be, well, we're going to have this Eisenstein series twisted by characters. So E zs chi is going to be equal to the sum gamma infinity quotienting gamma naught n of, and now there's going to be chi of gamma bar. This is chi of the lower right entry. of the matrix gamma, and then we're going to have imaginary part of gamma z to the s. And we're going to look at the left-hand side and the right-hand side of star, and we're going to construct both of them separately. So let's start by constructing the left-hand side of star. And we're going to define some generating function that I'm going to call v. So v of z is going to be equal to, and I'll also introduce some other notation that I'll use for this talk, where I write some squiggle, which means a bunch of factors that you don't have to care about. So this is going to be some gamma functions, maybe some L functions, or some Gauss sums, something like this, but stuff that isn't super important for the story this very moment. And then I'll take the Eisenstein series at 1/2 plus u comma chi, and then Eisenstein series at 1/2 plus v comma psi. So here this u, v, chi, and psi, these are quantities that satisfy the assumptions up here. And so these factors in front, these are essentially going to be the factors that complete these Eisenstein series so that they have a nice functional equation. And that's going to mean that this function v has a Fourier expansion. And the Fourier expansion is going to look like, okay, something in front of this constant term. It's going to be y to the 1/2 plus u, and then you're going to have a sum n not equal 0 to absolute value of n to the minus u, sigma 2u, and here I'm using the convention that when I say sum of divisors of n, I mean sum of divisors of the absolute value of n. So, and then here this will be twisted by character chi, and then you have this Whittaker function, and then you have this K-Bessel function, and then you have this e of nx, e to the 2 pi I nx. So that's going to be the first factor, and then it's going to be multiplied by the second factor, but of course just with u replaced with v and chi replaced with psi. Okay, so we have this Fourier expansion of this thing that, you know, if you want to be explicit about it, you could, of course, just multiply this out. And the trick that we're going to use to construct the left-hand side of star is to look at the kth Fourier coefficient of v. So this is going to be step 1. Let's look at the integral from 0 to 1 of v of z times e of minus kx dx, right? So this is the kth Fourier coefficient, and written out in this way, we can, by inspection, see what it's going to be, right? So either we take this constant term here, and we take e kx, this term here, so this term where n is k, or we take the constant term here and we take the term here where n is k, or we take n and k minus n. And when you do this, well, okay, you're going to get the stuff from the first two things where you take one of the constant terms, so I'm going to just write a squiggle for that. And then you have 4 times the sum n not equal 0 or k of sigma 2u n chi sigma 2v n minus k. So here I'm using the fact that these things are even in n, besides this Fourier coefficient at the end here. So you have the product of these two things, and then it's going to be divided by n to the u n minus k to the v, and then when we multiply the Whittaker functions together, we get a y times ku 2 pi n y kv 2 pi should be n plus k y. And this, you can see already that we've got the sum over n of this thing appearing, and hey, that's looking a lot like the sum right here, right? So we're making some progress. So this is step one, is to just consider the kth Fourier coefficient. Now step two is going to be to take a Mellin transform of this kth Fourier coefficient. So it's going to be the integral y from 0 to infinity, x from 0 to 1 of v of z, e of kx dx, and then dy over y for the Mellin transform. Or sorry, y to the s minus 1 dy over y. And of course, you could take this Mellin transform just at s instead of s minus 1, but things come out a little bit more nicely if you look at s minus 1, so that's what I'm going to put here. So this is just this Mellin transform of this thing above, and when you do it, when you get, okay, some junk plus some other junk times this sort of a Dirichlet series, n not equal 0 or k, so it's going to be the Mellin transform of this thing, and you still have this coefficient, sigma 2u n chi sigma 2v n minus k psi, and then here this n minus k in the denominator goes away. You're just going to get an n to the s plus u plus v, and the thing that's making this go away is this hypergeometric function, 2f1 of, okay, something, and then where you're evaluating this hypergeometric function is at, let me check very quickly where you are evaluating it. You're evaluating it at 2k over n minus k squared over n squared. So this thing, this hypergeometric function, you can look it up and you can figure out some of the properties. It's given by some series, and the takeaway is that this thing is going to be about 1. So it's some infinite series. The first term is 1, and then the second term and the terms onwards, they have this power of this quantity. So if n is large relative to k, and k is going to be a fixed integer, then those terms end up being quite small. And you have to do some analysis to really get rid of this thing, but I'm going to gloss over that. So in the context of this original thing, when I say x goes to infinity and all other quantities fixed, in the context of subconvexity bounds, what I'm saying is that this is what would be a subconvexity bound in the t aspect, and it wouldn't look at the k aspect, the n aspect, etc. Also not going to look at uv dependence, only going to look at the dependence in t. Okay, so the step 1 is going to be look at the kth Fourier coefficient. Step 2 is taking a Mellin transform, and then step 3 is going to be using Perron's formula. So let's take an integral, and here I'm going to be a bit loose. I'm going to write 3/2 minus it. So this is in the region of absolute convergence of this Dirichlet series, but you can do a little bit better. But just for the sake of illustrating, I'll use 3/2. And then, so you take the this Mellin transform you had from step 2, so the integral y goes from 0 to infinity, x goes from 0 to 1, v of z, e of minus kx, dx, y to the s minus 1 dy over y. So this quantity here in the middle, that's just this quantity. And then you're taking essentially an inverse Mellin transform. It's a partial inverse Mellin transform because you're thinking of t as being large but not infinite here. So x to the s ds over s. And this is going to give you, well, maybe not exactly equal to, but something like some junk times the left-hand side of this identity star, right? So it's going to give you essentially the sum of Dirichlet coefficients, right? Because if we look at the Dirichlet series, it's a series, Dirichlet series in S, and the Dirichlet coefficient is this product of sum of divisor functions divided by n to the u plus v. And so the 3 steps really, this one is the kth Fourier coefficient. This step is going to be taking a Mellin transform. And this step is going to be what's called Perron's formula. And the idea for Perron's formula is, well, I mean, let's just look at some simple complex integral. Let's look at the integral 1 minus I infinity to 1 plus I infinity, ignoring convergence issues for now, of y to the s ds over s. Here y is going to be some positive real number, and this is 0 if y is strictly less than 1, and it is 2 pi I if y is strictly greater than 1. And the reason why this is because you can, so if y is less than 1, you can shift this contour, just real part of s equals 1, to the right, and you're going to get exponential decay in your integral, and you're not going to cross any poles as you do this. So the value of your integral is 0. If you have y greater than 1, then instead you need to shift to the left. And there it's going to be the same thing. Your integral is going to decay exponentially, but you have a single pole coming from this denominator of s here. And so that's going to give you your 2 pi I. And what this implies is that this integral, say, sigma minus I infinity to sigma plus I infinity, where sigma is just some sufficiently large real number. If you look at a Dirichlet series and you write it as the Dirichlet coefficient times x over n to the s ds over s, this is going to be equal to 2 pi I times the sum n less than x of a sub n. And so that's why once we had this step 2, this Mellin transform, this Dirichlet series, after taking care of this hypergeometric function, we could use Perron's formula and get rid of this S dependence and truncate the sum just to n less than x, which is exactly what we have over here. Okay, so that is how to construct the left-hand side of our identity. Right, we do these 3 steps. We take the kth Fourier coefficient, take a Mellin transform of the Fourier coefficient, and then we use Perron's formula. One comment I will make is that, you'll often see, instead of looking at the kth Fourier coefficient, you'll see an inner product of V with this Poincaré series. So let me define this right now. So here, this Poincaré series, ZS, this is a lot like this Eisenstein series. It's a sum gamma in gamma naught n mod gamma infinity of, and now we've got the character as usual, but then we have an E of, is it plus K or is it minus K? I want to say it's plus K, but I may be wrong. So I'll chicken out and put plus minus. I think it's a plus here. So it's K times gamma Z, imaginary part of gamma Z to the S. So this Poincaré series is basically just this Eisenstein series, but with an E of K gamma Z. And when you take an inner product of your V with this Poincaré series, you end up with something that looks a lot like this. You end up essentially picking off some shifted convolution with some Whittaker functions. But the problem is that when you go to step 2 of trying to take the inverse Mellin transform, so this is for step 1, and then step 2, step 2 becomes or involves this Mellin transform K 2 pi n y with, I don't know, maybe this is U K V 2 pi n plus K y, something like this. E to the minus 2 pi ky y to the s dy over y. So maybe not becomes, but involves. And this is this is hard. You're not going to find this in tables of integrals. I found it in one, but it wasn't in a very useful form. And a lot of papers spend a lot of sections on analyzing this integral. It should be, n is going to be large relative to k, so ultimately this should be about the same as just if you had a product of two Bessel functions here. But actually approximating that properly, in principle, is straightforward, but in practice it's a lot of work. So a nice way around that is instead to just look at the kth Fourier coefficient directly, not to take an inner product with the Poincaré series. Okay, so that's it for the discussion about the left-hand side of this identity star. Now let's talk about the right-hand side of star. So the idea is going to be getting another expression for V. So if we can write this function V, which recall was our generating function, product of two Eisenstein series, instead of just looking at its Fourier expansion directly and then going through these 3 steps of Fourier coefficient, Mellin transform, Bernoulli's formula, if we can get a different expression for V and then goes through those same 3 steps again, then we'll get something different. So the way to do this is to use spectral decomposition. So spectral decomposition is the following, and I'm going to warn that I'm going to write something false right now, but let me write it anyway. So v of z is going to be equal to, and now there's going to be a sum over Moss forms fj. So when I say a sum over Moss forms fj, really what I mean is pick a complete orthogonal basis of Hecke cusp forms for the custal subspace of the space of automorphic functions. And what appears here is you're going to take this inner product of v with your Moss form. You're going to normalize by the norm of this Moss form, where here these brackets indicate the Peterson inner product, and you have your Moss form here. And then you also have this contribution from the continuous spectrum, as it's called. So it's some cusps frac A of gamma naught n, and then it's an integral, I'm going to write parenthesis 1/2 to mean real part 1/2 of this inner product of v with this Eisenstein series at the cusp frac A in the variable z, lambda, and here it's the character that appears. So v is an automorphic function of weight 0, level n, and character chi psi. So that's why there's this chi psi that's appearing here. You do this, and you multiply by the Eisenstein series itself. And then you have an integral. This is an integral in lambda. So here, v is an automorphic function of level n, weight 0, and character chi psi, which is immediate just from looking at its definition. And spectral decomposition for those functions, it looks like this. It's this identity. The idea behind this identity is that the idea behind spectral decomposition is that you can think of this as a basis, right? So Moss forms, and then plus Eisenstein series are a basis for and then I'll say the functions that satisfy this, the set of functions, the set of automorphic functions of level n, weight 0, and character chi psi. This is a vector space, and you can sort of pick a basis. Now, of course, this is not literally true, and you can't even really make sense of this as a literal statement. But if you just squint at it and pretend that this makes sense, well, if you had a basis for a space and you had this vector in your space, how would you express that vector in terms of your basis vectors? Well, you take the inner product, because remember, we assumed that this was going to be a complete orthogonal basis for the cuspal subspace, consisting of Hecke-Moss forms. And because it's a complete orthogonal basis, you just project onto the individual basis vectors and normalize appropriately and multiply by a basis vector, right? This is just linear algebra. And then here, it's more or less the same thing. Here, you can really take it quite literally. This is a complete vector space, but here you have some issues with normalization. So this is what you end up getting, and I think morally this is what's going on, but there's some analysis that that prevents you from taking this too literally. So so why is the above false? And the answer is that to do this, you need v to be square integrable in this as an element of the set of these automorphic forms. So I'm going to write as an element of the upper half plane mod gamma naught n, but with character chi psi. And this is not the case. In fact, the issue is that this term is going to diverge. So v inner product with the Eisenstein series equals infinity. And well, this is bad news, right? Because we can't do this, and this term is why we can't do this. But ideally, what we would do is we would break this down into 4 pieces: 1, 2, 3, 4, and ideally 1 and 3 are, I'm going to put quotes here, routine calculations. And when I say routine calculations, I mean, okay, you do something called unfolding. That's not so bad. And 2 and 4, you just look up. In particular, ultimately, what we want from this expression is to find the kth Fourier coefficient. So this is going to be some Moss form. You can write down its Fourier expansion however you want, and then for the Eisenstein series, you can just go find in the literature what the Fourier expansion is. But we need to solve this problem that v is not square integrable, that this inner product diverges. How do we do this? So the solution, and this is, I think, the most important new thing that comes from this theorem that we're talking about, the most important new idea is to use automorphic regularization. And I'm going to put some quotes around this. So the quotes I put in because this is a non-standard term. I've seen it appear in a few places, right? It appears in Takhtajan and Vinogradov, etc. But if you say automorphic regularization, people are probably not going to know what you're talking about. But here's the idea. So the genesis of the idea is, so you can look at, so in general, if you want to look at this inner product of, say, some function f with this Eisenstein series at infinity, you can look at this as this integral on, so this is the definition of the inner product. It's the upper half plane mod gamma naught n of f of z, and then the sum gamma in gamma infinity modding out gamma naught n of, here I'm going to, well, okay, chi of gamma conjugate, imaginary part of gamma z to the s, and then this is going to be all complex conjugate, and then the measure is dx dy over y squared. And in each piece, what you do is you make this change of variables so that you get just a z here. So z goes to gamma inverse z. And you're going to get this this chi of gamma inverse coming out. When you make this change of variables here, you're going to get something that cancels it. You're going to get a chi of gamma inverse coming out here that cancels the chi of gamma here. And essentially what happens is you end up unfolding the fundamental domain, meaning if you think about sort of the usual fundamental domain, and then for each piece you're making this change of variables, you end up tiling this strip of the upper half plane mod gamma infinity, right? So this is an integral from 0 to 1 in x and 0 to infinity in y. And then here you have, again, your f of z, and then you're going to have a y of s bar, right? Just this imaginary part here. And then dx dy over y squared, which is in fact the Mellin transform of the constant term of f. So this is maybe how you can think of why I put an s minus 1 above, because this is the natural thing that pops out. So this is how you normally take an inner product with your with an Eisenstein series. It's just the Mellin transform of the constant term. And this inner product of v with your Eisenstein series is going to be equal to, and then using the same idea, it's going to be this integral 0 to infinity of something times, well, okay, let's look at our function v. What is the constant term going to look like? It's going to be some power of y that you get from multiplying these two things together. So it's going to be something times y to the 1 plus u plus v, and then the sum n not equals 0 of this thing, right? So it's going to be something times y to the 1 plus u plus v plus sum n not equals 0, and then what is it? It's going to be 4 sigma 2u n sigma 2v n to the minus u minus v, and then y k Bessel of u 2 pi n y kv 2 pi n y. And this is always going to be times y to the s bar minus 1 dy over y. And this term is the problem, right? So if you just think about a Mellin transform of, say, y to the alpha dy over y, this is just, this diverges for every alpha. Either the tail is too heavy, or you diverge at 0, or in the case of alpha 0, both. So this is the problem. And automorphic regularization is the following. So is you can ignore powers of y where the real part of alpha is less than 1/2. Has to be strictly less than 1/2. And this is not at all obvious, but it is true, and this lets us take these inner products. So as references for these, I will say there's Zagier's paper from 1981, which is going to be level 1, it does this. And then if you want, so this is going to be level 1. The reference that's most appropriate for the stuff that I'm talking about today is this paper of Hulse, Juan, Lowry, Duda, I should say for the typesetting, right? This is in LaTeX 2 dashes, this is 2 dashes, and this is just 1 dash. So this is one person. And Walker, and then the paper is second moments of the Gauss circle problem, or moments in the Gauss circle problem, of the Gauss circle problem, I'm not sure, of the, and this is the appendix. And this is great because it's pretty down to earth, yet it's clearly amenable to the stuff they're doing here. So this is, I think this is a preprint from like 2017 or something. Then there's also, in more generality, this paper of Michel and Venkatesh, which does this automorphic regularization stuff in a lot of generality from 2010. And then there's also recent work of Han Wu that tries to expand even further. So this is an idea that you can generalize quite a lot, but the version that's most relevant for us is this this Hulse, Quan, Lowry, Duda, Walker paper. And so this fact is surprising. You can think of this essentially as a generalization of the Moss-Selberg relations, if you know what those are. But in this case, this is going to give us a way to evaluate this. So we're going to define this function r of z, and we're going to take it to be, let me see if I have it in my notes. So I'm going to take it to be something times e of z, and then 1 plus u plus v chi psi. And the idea here is that if you look at the constant term that we're getting, the power of y that we get, this is the power of y that we get. And by taking an Eisenstein series and subtracting it off, we're going to be, we're not going to have any powers of y that are too big. What is talked about in Hulse, Quan, Lowry, Duda, and Walker is that in fact you need to subtract something off that fixes all of the cusps at the same time. If you just only had to subtract one thing, you can just subtract this. You didn't really need anything too tricky. But because you have multiple cusps, you also need to worry about the other cusp, the cusp at 0. And so the cusp at 0, you end up having to subtract off e of z, u plus v, chi psi. And then when you look at the cusp 0 and you look at what constant term you're going to get there, this will cancel that. And because of our assumption, right, remember we assumed at the very beginning that the real part of u and the real part of v is strictly less than 1/2. What that means is that when we add this, we're not going to have to worry about this at the cusp infinity, right? Because that's going to fall under this class. Okay, and so that's pretty cool. And now the statement becomes that v of z equals r of z, and then you can do the spectral decomposition of v minus r. So it's going to be a sum over a complete orthogonal basis of Hecke-Moss forms for the cuspal subspace of, and then here's going to be v minus r inner product with f normalized times this Moss form, and then plus 1 over 4 pi I sum over the cusps frac A of gamma naught n, integral lambda has real part 1/2 of, and now you have the inner product of v minus r with your Eisenstein series at frac A times Eisenstein series at the cusp frac A of z lambda chi psi. And this is an integral in lambda. And this inner product, now we really can evaluate it using using this principle of automorphic regularization, that when we unfold all the powers of y that have real part of the exponent less than 1/2, we can just simply ignore. And we've chosen our regularizing function so that there are no powers of y which are greater than that. So this ends up, so this is, you can evaluate with automorphic regularization. So that essentially gives the right-hand side of star. Because what happens is you have these pieces, right, 1, 2, 3, 4, and now you can really evaluate them all individually and do the 3 steps, right? Take the kth Fourier coefficient, take a Mellin transform, and then use Pellin's formula, right? Take that inverse Mellin transform, right? Not literally using Pellin's formula because it's no longer Dirichlet series. And then you also have to worry about this 5, right? This regularizing function. And you still perform the same 3 steps, so same 3 steps of kth Fourier coefficient then a Mellin transform, and then Pellin's formula. Which again, you're not doing this with a Dirichlet series, but just stick it in and evaluate that integral however you want. And the main term of right-hand side of star comes from this number 5. Comes from R. And this is a general principle that, you know, I mean, certainly in all the cases I've seen, that the regularizing function R is the one that gives you your asymptotic growth. So the last thing to do is look at error terms. And looking at the error terms is kind of tricky. Essentially, when you have, say, this 1 and 2 and this 3 and 4 thought of together after you go through these 3 steps. So you have to bound you know, the term 1 plus 2, right? So when I say 1 plus 2, I mean this whole term. After the 3 steps, these 3 steps. And you get some expression. It involves a sum over Moss forms, and then you have something like whatever the first Fourier coefficient of your Moss form divided by the norm of that Moss form, and then you have this this L function of the Moss form. Let me write it this way. This L function of something times the Moss form. Actually, there's a conjugate here. This is going to be like some Dirichlet character. And then you're going to have some gamma functions in both the numerator and denominator. And this is a sum over Moss forms. And the way that this goes is using what's called a spectral large sieve. And it's quite technical. Essentially, it amounts to the Lindelof hypothesis on average. And this is yeah, it's quite technical. So I don't want to get into it right now, but I'll get into it in some future videos. But when you do this, you end up bounding this error term, because remember the main term is going to come from this regularizing function, and then these are going to have some growth in t, and then you balance your error terms, and you end up getting this main result. So this O of this amount that you're subtracting off, this is coming from the spectral large sieve.